Another use of limits is to use it to find the area underneath a curve. For instance, here's your typical parabola, y equals x squared, and I have here this triangular region, this one, kind of looks like a triangle, except that the third side is not a straight line, it's a curve. And you might look at this and think about, what do you think the area of that is? You can push pause and think about that if you want. Okay, you might have come to the observation that if you were to connect those points and actually make an actual triangle, this would be base 3, height 9. So that green triangle would have an area of 13.5. So the blue area would be something less than 13.5. But how much less? Well, we're going to learn how to do that in this video. I'm going to start with a question we already know the answer to. What if the curve itself was the line y equals x? And now this was 3, and that was 3, 3. Well, we don't need a fancy method for that. That actually is a triangle. So the area is 1/2 of 3 times 3, which is 4.5. But what if I didn't know the area of a triangle formula? What if I only knew the area of a rectangle formula? How might I still find the area of this triangle? We'll know the answer is right if we get 4.5. One way I can approximate the area of this triangle is to split up the x-axis between 0 and 3 into, let's say, 6 evenly spaced intervals. So here's 1, 2. So now these points are all at like half. This is 1. That's 1.5. That's 2. That's 2.5. And now I'm going to do something kind of funny. I'm going to make these, from each of the points, I'm going to make a vertical line straight up until it hits the curve. And then I'm going to, from the right-hand line, I'm going to take that top right point and kind of go like that to make a rectangle. I have another rectangle. And you can see what I have now are 6 rectangles. And the sum of the areas of those rectangles will be bigger than the triangle, but not that much bigger. And if there were even more rectangles, they would be, if the rectangles were even skinnier, let's say there were 100 rectangles, then it would be practically the triangle. And if there were an infinite number of rectangles, it would be exactly the triangle. So that's the insight. Well, let's go with this real specific question with the 6 rectangles. Each of these rectangles, so the combined area of these 6 things is base times height for each rectangle. Now, each rectangle has a base of 1/2. So 1/2. If you don't mind, I'm going to start from all the way on the right. The first rectangle has a base of 1/2 and a height of 3. Actually, I hope you don't mind. I'm going to go back to starting at the left. The left-hand rectangle has a base of 1/2, and because this x-coordinate is 1/2 and the line is y equals x, this y-coordinate is also 1/2. So 1/2 is the height of that first rectangle, which happens to be a square. The second rectangle also has base of 1/2, but the height is based on this y-coordinate, which is, this is 1, 1, so it's like that. And the bases are always 1/2, but the height changes. The height goes up each time. 1/2 times 2.5. So those are the 6, 1, 2, 3, 4, 5, 6 rectangles. Now, if I were to make all these rectangles areas, all 6 of them, into fractions and we give it a common denominator, I would get this expression. And notice how they all have fourths in there. So if I were to factor that out, I'd get area equals 1/4 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. And I could add these all together. And this one ends up being 21, and it ends up being 21 over 4, which is 5 and 1/4. Now we know the actual answer is 4.5, so I'm not surprised this is bigger. But that's the idea. Now, if there were a lot more, before I get to that, I'm going to remind you that instead of adding 1 plus 2 plus 3 plus 4 plus 5 plus 6, there is a formula where if you add together the first n integers, it's n times n plus 1 over 2. So in this case, it's 6 times 7 over 2, which is 21. So that formula might come in handy. That's the formula for the sum of the first n integers. Now what if, instead, I still had a 3 here, but now I made these rectangles really skinny, so there were 100 of them. Well, the area, the very first rectangle, they would all have a base of 3 over 100, because 3 is the entire thing. I'm cutting it up into 100 intervals. The first interval, this bottom right-hand endpoint would be 3 over 100, and the second one would be double that, which would be 6 over 100, and the third one would be 9 over 100. So that's not only the x-coordinate of the bottom right-hand corner, but it's also the height of the rectangle, because it's y equals x. So this 3 over 100 is the base, and the first rectangle's height is 3 over 100. Second rectangle has a base of 3 over 100, but a height of 6 over 100, and so on. 9 over 100. All the way up to the last, which would be 300 over 100, which is the same thing as saying the last rectangle has a height of 3. Now I'm going to do one more step, the next step. I'm going to rewrite this 6 over 100 as 3 over 100 times 2. And I'm going to write this 9 over 100 as 3 over 100 times 3. And this last one, this 300 over 100, all right, it's 3 over 100. That first one's the base, times 100. Now notice how all these have these two 3 over 100s, so I can actually factor that out. And inside the parentheses now, when I factor that out, let's put a 1 here, we'll have these integers, 1 plus 2 plus 3 plus dot 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 plus 100. Well, using so I have 3 over 100 squared, and this we have a formula for is 100 times 101 over 2. And if you pop this into the calculator, you get 4.545, which is pretty close to 4.5. But you might say, well, I want to get exactly 4.5. Well, we actually can do that. But for that, these rectangles would have to be so skinny that there would be an infinite number of them. For now, I'm going to call the number of rectangles n. That way I can get a general formula for whatever you want to make n, whether you want to make it 6 rectangles or 100 rectangles, or whatever number you want. And we'll see that will include n equals infinity. So what happens here is that each rectangle has an area, has a base of 3 over n, because there's n rectangles, takes up 3 altogether. And this very first rectangle has a height of 3 over n. If you don't mind, write 3 over n times 1. The second rectangle has a bottom right hand corner has an x-coordinate of 6 over n, because it's double the 3 over n. I'm going to write that 6 over n, which is also the height, as 3 over n times 2. And this would continue all the way up to 3 over n times n. So I get 3 over n squared times 1 plus 2 plus 3 plus dot 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 up to n. But there's a formula for that. And here, this 3 over n squared times n plus 1 over 2, that works for any value of n. So if I were to plug 6 in for n, I would end up with 5 and 1/4. And if I plug in 100 for n, I would end up with 4.545. But can I plug infinity in for n? Well, if you plug infinity in for n, you would get infinity over infinity, which is not having a value. However, we learned in an earlier lesson, I can say what's the limit as n goes to infinity of 3 over n squared times n plus 1 over 2. To make this look more like what we've been doing, and I'll even go one step further, although you won't need to do this full simplification, but I think it will help us understand 9n squared. Oh, see this 2 over here, I forgot that. 9n squared over 2n squared. Well, we learned a couple of lessons ago that when the limit goes to infinity and the powers are equal, the answer is just going to be the ratio of the two coefficients, which is exactly 4.5. Now, I could go even more generally by taking the line y equals x and just calling this last point x. And if I did the same process, now the width of every rectangle would be x over n, and the heights of these triangles would be x over n times 1, plus, that's the width there, x over n times 2. The next one, would be base is x over n, the height is x over n times 3, and that would go up until x over n times n. But when you put all those things together, let's come up here for it, I'd have x over n squared, I factored that out, and 1 plus 2 plus dot 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 up to n. That would turn into x over n squared times n plus 1 over 2. Now we can take the limit as n approaches infinity of x over n squared times n plus 1 over 2. That x is a little confusing because that's a variable also, but we're going to treat it like it's a constant. And we can see here that the numerator is going to be, I would say, approximately x squared n squared over 2n squared. Those are what the lead terms would be. So because the powers are equal of the ends, you get x squared over 2. And I know this is a very long way of showing that the area of a triangle is x squared over 2, something we knew a long time ago if it was a right triangle, 45, 45, 90 right triangle. But this method is going to be really powerful when we make a slight change, which is to change the curve to y equals x squared instead. Let's do the specific, the 3, 9 situation. Now, if I were to split this into, let's say, 10 rectangles, I actually want to split it to 6 rectangles. Well, these rectangles do all have the same width. The width is 1/2 in this case. But the heights, the first rectangle's height is not 1/2. That's the base is 1/2. The height is going to be 1/2 squared because this curve is y equals x squared and this point is on the curve. And the second rectangle, this bottom right corner is at 1, which I'll call, if you don't mind, 2 over 2. And that makes this thing 2 over 2 squared. And this is going to go up to the last one, which is going to be 6 over 2 squared. So the bottom right corner is 1/2, 2 over 2, 3 over 2, 4 over 2, 5 over 2, 6 over 2. But since it's on the curve y equals x squared, this happens. Now, I'm going to rewrite the 1/2 squared as 1/2 times 1/2. I want to write the 1/2 as 1/2 times 1, and then square that, so it becomes 1/2 squared times 1 squared. Now if I take this 2 halves and rewrite it as 1/2 times 2 squared, and then kind of distribute the square through, I get 1/2 squared times 2 squared. And it would go up to 1/2 squared times 6 squared. Now these each have 1/2 to the thirds. Oops, I left off the base here. So if I factor out the 1/2 to the third, I end up with the area is 1/2 to the third times 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. Now most people don't know that there is, just like there's a formula for 1 plus 2 plus 3 up to n, there's a formula for 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared. And it actually starts off n times n plus 1 just like the other one, but then it has this mysterious 2n plus 1, and the denominator is not 2 or 3 but 6. So we'll just say that that's a formula that we're not going to prove in this video. Now if you plug 6 into this formula, you end up with 6, which would cancel out with this 6, and 7 times 13 is 91. So we end up for this thing, we get 90, this 1/2 to the third would be 8, so 91 over 8, which is a little bigger than 11. But that's going to be bigger than the actual answer, because these rectangles, you see how they kind of go into this region here outside of the curve? So what I want to do is make more rectangles. And I'm going to jump to the general case with the, not total general, I'll still use the 3, 9 situation. But now I'm going to split it up into n rectangles, and presumably n's a really large number. So when that happens, each rectangle's width is going to be 3 over n. But the heights of the rectangle are going to be 3 over n times 1 squared. The width is 3 over n of the second one. The height is 3 over n times 2 squared. And that's going to go all the way up to 3 over n times 3 over n times n squared, which is going to become eventually 3 over n cubed times 1 squared plus 2 squared all the way up to n squared. But we have a formula for this, so let's just move over here. It becomes 3 over n to the third times n plus 1 times 2n plus 1 over 6. Now for that formula I could put any value of n I want. If I want to know what happens with 6 rectangles, I put 6 in for n, and I'll end up with this 11 point something. But best of all, if I want to know the exact answer, I can say the limit as n goes to infinity of 3 over n cubed times n plus 1 times 2n plus 1 over 6. Just to make this easier to see, the denominator would be 6n to the third. That's 6, and this n to the third. And the numerator would have 3 to the third. And this thing is a complicated expression, but it's definitely going to have 2n to the third as its leading power. There is other stuff, but that other stuff isn't going to really matter, because when you take the limit to infinity, these n cubes are all, the highest degree term is all that matters. So we end up with 3 to the third times 2 over 6, which is the same thing as 54 over 6, which is 9. And 9 is the answer. Remember back from the warm-up, we knew that it was something less than 13.5, but it turns out that it's exactly 9. Now, if I want to go even more generally with y equals x squared, I'm going to call the last point x comma x squared, and still make n divisions. When I do that, I end up with x over n. I'll just jump x over n cubed times n plus 1 times 2n plus 1 over 6. For that, I could put any value for x and n in. But if I leave it as an x and I do the limit as n approaches infinity, I'll get x cubed times 2n squared. There's other stuff, but I'll ignore that other stuff, times 6n cubed. Sorry, that's 2n cubed. And we end up with x cubed times 2 over 6, which is x cubed over 3. Now, if I want to do other curves, like y equals x cubed, well, for that, eventually you would need to know the sum of the cubes formula, which I'll just tell you. It's the same as the sum of the integers formula, n times n plus 1 over 2, and then put squared. And if you found the area of this thing, you would actually end up with x to the 4th over 4. And you might notice there's a little bit of a pattern. When it was y equals x, the area was x squared over 2. When it was y equals x cubed, the area was x sorry, when it was y equals x, it was x squared over 2. When it was y equals x squared, it was x cubed over 3. And when it's x cubed, it's x to the 4th over 4. Suggests that if I kept going, I would probably get x to the 5th over 5, or in general, the area will be x to the n over n, where x is the rightmost point, and, sorry, yeah, this n is not the n for the number of rectangles. I'm going to call that a different thing. I'll call it m. Because we already have an n in this problem for the number of rectangles. This x to the m over m is what would happen if I made n equal infinity. And that is yet another use of limits.